All right, so welcome everyone to another OCP Tap call. This is call number 101, actually. And today we have the honor to have Professor Ken Bierman. Ken has worked in distributed systems since getting his PhD at UC Berkeley in 1981. He's currently the Rama Rao Professor in the Department of Computer Science at Cornell. Past project including building the infrastructure that operated the New York and Swiss Stock Exchange, developing the core architecture and software for the French air traffic control systems, and inventing some of the techniques that enable today's scalable, self-managed cloud computing settings. Ken is a fellow of the ACM and IEEE and won IEEE's Kanai Award for his research in distributed systems. So today's talk is about, I mean, we changed it multiple times, but I think the last title we have is, does accurate time matter for tasks that need consensus? And with no further ado, Ken, the floor is yours.
Well, thank you so much. And for those who are attending, let me just say that I had no idea that I would be starting your next 100 talks, and I hope it's one that you don't miss later to come back to and so on.
Oh, we
So,
definitely are honored.
okay, great. I'm Ken Berman. I've been working in this area for a long time, and what I wanted to talk about is whether accurate time should come first or second in tasks that need a form of agreement. So does time actually matter for consensus? And to set a context, what I'll do is set this in a very concrete situation, which arose in 1996. At the time, I got a telephone call from someone who turned out to be the Minister of Transport in France, who asked if I would work on the French air traffic control system. It was a very peculiar call. It was in very formal French. He told me normally they would only consider having a French person work on this, but he'd make an exception because my wife is Belgian. So I pointed out that Belgium is not France, and he said, oh, but the French part of Belgium, we should never have given it away. So I came to work on the French air traffic control system, and Flavia Christian and a team from IBM were consulting for L'Oreal on the American one, and that was the race from my point of view. And of course, air traffic control centers on many of the kinds of things a distributed systems community has to worry about: replication, consistency, fault tolerance. So I'll just run through the architecture first of the design that we came up with in France, but with a hole in it that I'll fill later. So obviously, you have radar coming in, and the radar is essentially like a television channel. You have a set of controllers. The French ones tend to work in teams. You literally could have 5 people cooperatively looking at a single system state and playing different roles. The American air traffic controllers tend to be more independent, and they just own something, which in 1996 was causing overloads. Ronald Reagan at the time had fired actually a large number of controllers after some sort of a job action that he got very angry about. So the American system was perceived as kind of melting down. The French one was a reaction to the fact that the Americans were going to rebuild, and they wanted to make sure that France was still a player. So, however, they didn't have the kind of budget. And so what I'm going to show you was built very incrementally. But the basic idea is that you have a single controller responsible for each runway and for each flight. There is a replicated database that has to maintain strong consistency with the current version of a given flight plan. And one of the invariants of the system is that no action can ever be taken other than against the most current correct flight plan. So the controller who authorizes a plane to climb 1,000 feet is actually creating version 14 of flight plan such and such. And if that's not the current version, that will be rejected, and they'll have to retry. And so it's a pretty strong invariant. And we're going to use a form of state machine replication internally. But in fact, there tended to only be one primary and one backup in that architecture. A message bus that talked to a whole bunch of apps, actually. By now, as they've grown this system out since 1996 when it was deployed. This is still in use. This has become an extensible set. And you can think of these apps as advisory. They read new flight plan data, think about it, and then different apps can sort of inject different opinions, but the apps don't ever change the critical state of the system. And then there's a broadcast service. And so the notification that there's a new version of a flight plan comes out from there, and anybody who should have a correct copy receives it in a kind of pub/sub manner with a strong semantic. And France has 5 air traffic control systems and also talks to England and Switzerland and Spain and Portugal and Italy. And so you have to talk to surrounding air traffic control centers. So here you're seeing the crux of a modern air traffic control system. There's a new version of this being built now in France called the 4-flight system, and it has almost the same architecture actually. And there's an app contributing an opinion. A typical app, I was kind of horrified to be told about this, is you've got some VIP flying in and they tell the pilot, you know, that VIP is going to have a tough time with their connection, but for only $250, Delta can land 5 minutes earlier and that connection will go much more smoothly. So they're literally starting to extort money for which landing slot you get. And in the FAA system, it's very similar. The main difference being at the time that the FAA threw out their existing system and said they would build from the ground up. What I showed you for the French system was really built incrementally with a series of piecewise development steps. And so it was a somewhat more constrained development effort, which in retrospect prevented us from crazy, if you'll forgive me, flights of fantasy, which is what actually, unfortunately, happened with the FAA system. So from a technical point of view, the person analogous to me in the FAA project was Flavio Christian, who was a wonderful, wonderful person. Remembering Gordon Bell, I remember Flavio, who died of a rare cancer not that long after I met him, but he was the architect associated with the core of the system. And the reason he was picked for that role was, of course, he was an IBM employee, and IBM was a major consultant to this, but also because his name was on this particular paper. So people call it the CASD protocol or the Delta Atomic Broadcast Protocol. And the idea was to develop an atomic broadcast solution in steps, starting with a very simple echo-based reliability protocol and then working its way up to a full-scale Byzantine agreement. And I'm actually going to show you that protocol. So the central concept here is going to be to synchronize clocks to high accuracy. We're going to end up building something that's basically a database called a Delta Common Storage. Dale Skeen was responsible for that, but it's layered over the broadcast, and we won't talk much about the database. But the idea was going to be then that you had a high-level API based on database transactions. The transactions are against a kind of real-time database. Delta will be the real-time bound on it. And then, of course, we need rapid reactions. And so the constraint of time comes in that you need to react to an event within about 100 milliseconds. And then there's a set of assumptions introduced. What I'll say is that none of them are surprising. You have a small subset of the system permitted to fail at any given moment. If a lot fails, we shut the whole system down. You have high quality hardware clocks that we can normally trust, but of course, sometimes clocks can fail. Messages are quite reliable, but this was 1996. So you had a non-trivial loss rate because that's how flow control was implemented. These days, we have hardware networks that offload TCP, but actually also don't drop packets and do other things for flow control. And that changes, and you can start to talk about loss rates as low as the backplane on a multi-core processor. RDMA, for example, is at that range. But in those days, because flow control was through an active process of dropping messages, the rate wasn't that small. And then you have various forms of crashes, but we're thinking in terms of halting failures. Even when they go to the Byzantine case, they really mean Byzantine clock failures. We'll talk about that in a second. So here's the protocol in a nutshell. It's pretty simple. In their system, they'd get some kind of an event. A pilot requests to change altitude for some reason. Controller wants to approve that. And so you take the current flight plan, you mutate it, and you would broadcast an update. And then to compensate for possible failures, everyone echoes what they got. And these messages are signed, so we don't have to worry about message corruption. There's a delay, which we're going to calculate, that's supposed to compensate for worst case outcome. And eventually everyone delivers messages and updates their storage. So why do we wait for delta time? Well, various bad things can happen. And if you think very pessimistically, Murphy's Law, you could say, well, in the first stage, it might be that the original sender was faulty. And as a matter of fact, each of the relaying processes could have been faulty too. They need to be reliable enough that the message didn't just evaporate from the system, but you can construct a worst case relaying sequence. And then you can say, now, wait a minute, we haven't really used up our budget of failures for the network either. And so you can now start to inject worst case network behavior for correct senders. And by the time you're done, you've used up your delta. So this is an illustration of that with some failures, and the red line is supposed to represent processes that failed against our budget of T failures or F failures, whatever I called it. Dash lines, who knows what a faulty process does, certainly could drop packets. And then eventually a legitimate sender, a correct sender, manages to try to send but has a message loss event. And here's a message perhaps that took a very long time to travel through this network because we're supposed to have assumptions on delay. And so that's where delta came out of. And to come up with this version of delta, you have to crank the math. I just talked through this slide, but basically the way they thought about the protocol was use up each budget of failures in an order which makes evident the very worst case admissible delay. If you have two messages, there are more that are concurrent, what we're going to do is use the sender timestamp, capital TA and TB in this example, to order them. If there was a tie, which isn't really very likely, you would break it with sender IDs. And so here we've got the blue message below before the red message at all the receivers. And then using the math, the paper develops the values for the different constants that are derived from more basic inputs, capital delta basically as a function of small delta, which is the worst case message delay, and these other parameters. Now, we've omitted that this was intended to be a real-time system. And so they felt that, well, okay, what they should really do is to guarantee that everybody who is correct delivers a message in the same order and within a bounded time window. And this introduces some complications, it turns out, because the CASD folks believed correctly that clocks can be faulty. A faulty clock in hardware has certain kinds of odd behavior. It's far more likely that a faulty clock has a bit get stuck than any other type of error. It's kind of hard to get a clock to run at the wrong clock rate. So it's far more likely that what it just does is doesn't count correctly. And that can cause time that just sort of oscillates back and forth. You climb up to some value and drop back to zero. Time can seem to go backwards, basically. So they had to think that through. And also you have to worry about clock synchronization failures, which can cause otherwise correct clocks to have too large a skew. And in fact, they ended up with a protocol where certain messages are recognized by the correct processes as being impossibly early or impossibly late, and are uniformly rejected. And in some cases, you might accept a message that came from an incorrect clock, and you end up with something like this. Same picture as before, but now there's a tau. I've shown it as tau A, which represents the target delivery time. And we will know that the message was applied to the delta consistent database within plus or minus epsilon, which is again a calculated window. And if we had two of these things happening, it would simply be that there'd be two windows. Now, of course, individual correct processes, one might be at the close end of the window, the other might be at the far end of the window, but the ordering will be respected in all cases. So they never relax that requirement. Okay, so this is the delta T or the CASD protocol in a nutshell, and it works. So if you're a Murphy's Law believer, then you can throw your grab bag of adversarial events at this protocol, and nonetheless, messages are going to come through in order. They're going to come through roughly at the right time, and we can take advantage of those properties as we design our air traffic architecture. But there is a problem. I don't know, Ed, if you were a participant in, I mean, this is right in the middle of your community, but there was a thing called BizBiz when I was a PhD student at Berkeley that was down at UC Santa Barbara or Santa Cruz. And I don't remember you being there, but you might have been. And it was either Jim Gray or one of the students in the audience who raised their hand at some point around here. The actual protocol was being presented there to the people who were present, and basically said, this is awesome. How big is delta in practice? So a little group went off to the side and calculated and came back and said, well, for reasonable assumptions, we've come up with, and I'm remembering the number actually, it was 3 minutes and 11 seconds. And now this is a problem because
what could go wrong?
Right. So any air traffic control event would have to run through this to get replicated fault tolerance. And so even the minor thing, the pilot asking permission to climb 1,000 feet takes 3 minutes and 11 seconds to get to the controller, as will their response. Of course, that's a disaster. And it's a well-known phenomenon that the theoreticians can't be allowed to run free range. So the vendors scrambled. L'Oreal and IBM put a kind of cost engineering effort in place, but here it was temporal costs. And what they basically said was, look, in those timing diagrams, it's obvious that delta is much, much too big. It's extraordinarily improbable that every bad thing will happen in order, in sequence. So they started coming up with different, arguments that can't happen. If you're going to get one process crash, it's probably not also going to have a maximum length delay on a message sent from a different correct process to a correct receiver, things of that type. And it kind of worked. And there's a lot of talk at the time about how engineers are the heroes. And that those theory people can do kind of crazy things, but you got to rein them in by having the engineers work over their stuff afterwards. And so, in effect, you took this thing where you had observed that really everybody does have the message right around here, and you've dropped delta to be as close to that as you possibly could. And this works. It does work. And so now they were up and running again. But now something bizarre happens. So I don't know if you know the movie that's Bette Midler I forget what it is, Three Witches. They're all kind of cute witches, but accidentally revived. And she's constantly cursing people. So this project seemingly was cursed. Everything had been working just fine up until then. But once they fixed the value of delta, and they were fixing a lot of things, so I don't know if they even initially understood what was happening. All of a sudden, bizarre bugs began to surface all through the FAA project. I heard about this because I was working the French project, but mostly because one of my colleagues, Fred Schneider, got called in to try to rescue them. And he was giving lectures on how to do proper, transactional systems and verify code. But this code didn't seem to verify properly, in the sense that you could verify it and yet it was malfunctioning. Even simple things that had been working fine, now suddenly these databases were diverging. Huge panic, there were gigantic cost overruns. And as a matter of fact, they canceled the project. Now, why did that happen? Fundamentally, it happened because, now I'm doing this in the rapid version, it happened because CASD never really has an agreement mechanism in it. It's entirely based on a whiteboard analysis, in where you take all these constants and you crank through, and you end up concluding any correct process that sends a message, every other correct process is going to receive the message within this delta. And therefore, you don't really have guarantees for a faulty process. And in fact, if a process is faulty in a kind of half faulty way, for example, maybe its clock fell out of sync, but now it fixes the sync. It runs NTP successfully. And possibly you pushed the protocol so hard that a single round of the network time protocol failing is enough that you could slide out of sync. Well, that process had a skew of 2.5 milliseconds. It was not allowed to be more than 2. And as a result, temporarily it was faulty. Well, now all bets are off. And it doesn't know it was faulty, because the adjustments that the time protocol make that bring it back into skew, it might not even be its clock that got adjusted. It could be all the others, right? So there's no guarantee that you know who is faulty. There's no guarantee that they crashed or anything remotely like that. They could perfectly well be participating. And so these technically faulty processes, once that happens, are kind of never considered to be correct again. So here's a picture of that in action. By the way, sorry about my a little bit of ozone in the air. I would say it was coming from Canada, but I wouldn't want to insult our Canadian colleague. So, so red is supposed to be a faulty process, but again, no one knows except God. So as it happens, this air traffic controller's console is somehow considered faulty. Maybe the other one too. The original rounds run, delta elapses, and errors start to occur. I dragged the delta out again. Here you've got somebody who delivers one of the two messages, but not the other. Here you've got somebody who delivers both messages, but one of them out of order and way earlier than anyone else. Could that happen? Yeah, with clock drift and skew, these are not unreasonable bad cases. And so now suddenly it should be obvious why they had this wave of bugs occurring. When they changed the temporal characteristics of their core communication bus in the system, it ran fast enough, but it was no longer guaranteeing any kind of distributed coherency, any kind of distributed coordinated property. This is just a reiteration. In my courses, I do that a lot, but I'll skip it for you. So, and so that explains the odd problems. The situation was so unlikely in the initial parameterization of the system when they initially debugged their work that you could never have observed a problem of this type. So they never did, and they were able to debug their code, and they had gotten things running. But as they squeezed the protocol, this intrinsic behavior becomes very evident, because it's no longer improbable that you'd have sequences of failures, that Murphy's law really would apply. And to make matters worse, once a process is faulty, there's no mechanism to heal it, because nobody's even detected that it's faulty. Dale Skeen and Fred Schneider started looking at ways to vote, or ways to somehow read the values of a sufficiently large set of replicas, Paxos style, right? Read a whole bunch of replicas and merge them in some way, develop another mechanism that somehow compensates, but they never got that to work. And this is America. We have big budgets, and so in the style that Winston Churchill summarized so well, we just built another one. We threw that one away. You can fly safely in America. It's not a big deal. My system is still running. You can start to worry that maybe the place where you're less safe is France, because it's about time that they upgraded to something where the person doing the work isn't close to retiring, right? And where you could actually maintain the software on modern hardware. I don't know how they do that, but they're still on my system over there. But on the other hand, I've been told by them that they've never had an issue in that system since it was first turned on, which is pretty amazing if you think about it. So what was the core difference? Well, core difference is that I'm a Cornell faculty member. And when I came here, I was more focused on sort of BSD style hacking, Unix style hacking. But then I came under the influence of Fred Schneider. And Fred was very close to Leslie Lamport. And Lamport, of course, in that time period, was pushing for consensus, causality. My software started using causality and causal ordering as a tool. They introduced it as theoretical, but I thought, well, we should implement things like that and use them. And in fact, consensus-based mechanisms are at the core of the software I designed. So here, nice picture of Leslie. He has a slightly sour look. That was probably because when he got his Turing Award, he started complaining that it took them 10 years too long to give him the thing, and they should have just recognized the inevitability of it and done it at the beginning. At one point, I'm a friend of Leslie's, and I was telling him, well, in a relativistic sense, maybe he got his Turing Award far earlier than most people realize. Anyway, he was a relativistic particle physicist before he moved to computer science. So if you remember Leslie's early paper, time instead of timeout would be a good example. And time clocks and ordering is another one. These around 1986, he was saying, well, if I reason about time, I end up in a kind of CASD style stew. He said, in contrast, if I send you a message and you acknowledge it, I know that you have my message. And I can reason on the basis of this information pathway that's been established. One leads to epistemic logic, to knowledge about events and their sequencing. The other leads to CASD, sort of a unilateral analysis where we just say, after this amount of time, this should be the state.
Kind of a rebel without a causal.
That is true, exactly so. So consensus, you know the problem. The version of it is this. Everybody's got a bit.
Yep.
Do we want to approve the school budget or not? And we run a vote, and it has to be a fault-tolerant vote. Somebody might not turn up to vote. To count the votes and reach agreement where every correct process does the same thing. It's a value that really is a vote that was cast. And there's no rule that it should be the majority, actually. So state machine replication is then built on consensus. And what we do is we take our data, put it in the same state initially, or if somebody's joining, we have to initialize them to a correct state. And then the same updates done in the same order by determination of processes, and we stay in the same state. Really, CASD was trying to achieve that, but it was trying to achieve it using a building block that didn't have the underlying consistent integrity that we need. In order to achieve that, we build protocols and reason about them using epistemic logic. And in fact, knowledge logics became an entire research area. That would be Joe Halpern, Yoram Moses, who's a good friend of mine. They began to introduce temporal operators when we reason about protocols and argue that when we prove things about our protocols, we ought to use proofs that talk about eventually. Or all processes know something. I know something, you know it, we all know that I know it. And they had
I like to say, I know what you knew.
That's true too. Yeah, and so there's sort of a local deduction, learning from someone else through a message. And then I can talk about me knowing that you received that message. However, there are some famous epistemic puzzles. So for example, if my wife and I met at Berkeley, so if Anne and I were going to eat indoors if it was raining, but outdoors if it was nice, and one of them is sort of the default, and then one of us has a windowed office, the other doesn't, you send her a note and say, it's beautiful out. It's always beautiful in Berkeley, so of course we should always eat outdoors. Well, but I don't know that she got my note. If she acknowledges, she doesn't know that I got her acknowledgement. You can build crazy outcomes in which two logicians in Berkeley never ever managed to eat outside, no matter how nice the weather is. unless you get the default right. One
You're
thing to learn
referring
is
to
you can't-
specifically common knowledge paradoxes.
That's
correct?
right. They're all common knowledge. And this is one of the limitations, right? And so CASD has its limitations. Common knowledge has its limitations too. You can't build common knowledge except in a sense that I'm about to show you. Now, most people would agree that this is horribly boring stuff to really do. When Leslie Lamport introduced TLA Plus, said that we should prove protocols like pqst using TLA, those of us who tried to follow that path, we all hated it. Leslie came and spent a summer working with us, integrating his models with mine, which was called virtual synchrony at the time. We came up with a beautiful, nice integration. Dalia Malki was involved and Robert Veronese. Then Leslie said, unless you prove this stuff, you being me, using TLA Plus, he didn't want his name on the paper. So we ended up writing a paper with 4 of us and not the 5th, because we just couldn't stand doing these proofs in TLA Plus. It was horrible. And you can integrate a kind of a knowledge layer over TLA Plus, but it doesn't help all that much. It's still horrible. Now, you get the further problem of FLP that you can prove safety in the sense that the system never violates its specification. It's invariance. But FLP shows that if you have a correct consensus protocol, you can kind of pump it in a way that prevents anyone from ever reaching agreement. And it involves intercepting certain messages, because there's a rule for how you identify these messages, delaying them until a certain state change occurs. There's a rule for how to recognize the state changes occurred. You have to have perfect vision into the entire system. And then you have to iterate this or else you run out of processes. You have to free up the delayed messages and then do the same thing with some other message that should be delayed. It's absurdly low problem. I mean, it's just impossible to produce this attack. I once had a student who tried to build it in a lab just for fun, gave up. However, nonetheless, it still establishes that you can have safety but not termination. And if you look at people who have proved the correctness of consensus-style atomic multicast or other types of leader election protocols, things of that type, what you find is that they have to work around this if they want to end up with what we would consider a total correctness proof. And interestingly, they do that by introducing the same kinds of assumptions that CASD does, and even introducing a little leap of faith, because you can't reason probabilistically about epistemic, the type of epistemic logic that Leslie argued for. You could have a different probabilistic epistemic logic. In fact, people like Justin Su in programming languages are working on that kind of thing today. But you can't get there in the old style. And the way you get around that is that you introduce these extremely high probability casting guarantees, but you only use them to rule out an infinite delayed FLP attack. And now you can prove termination based on that. And in fact, it's not even so boring anymore. So as an example, Annie Liu, who's at Stony Brook, has a distributed algebraic framework. Actually, I guess she really means distributed algorithms, but it's a play on words because it's also a distributed algebraic framework based on coalgebras, where what she's able to do is to take a specification extractable from many of these kinds of protocols, formalize it, and she has push button proofs of their correctness. And this has been done in other settings too. Daphne is a programming language variant of Java that was done at Microsoft. And Daphne has protocol proofs built into the equivalent of an extended type checker. So these days, it's not so boring. And in my work, we use these tools. So we go back to the French system. Even way back in 1996, I was using these methods, using something called virtual synchrony. And the idea of virtual synchrony was reach consensus on the membership of the system, run in membership epochs. That's what virtual synchrony specifically meant. Each epoch, it has a membership. We needed a word for the set. I took a database term. Databases have this notion of materialized views. So we call them virtually synchronous views, membership views, sort of like a database of membership, and you've got glimpses of it. And you end up, here's time still going left to right. And so this system, for whatever reason, P was the only official member. Then Q joined, got synchronized to P. That's called state transfer. Then R joined, now we had 3. Eventually Q crashed. And you can see that each event is associated with a reconfiguration, a new membership view. So this is consensus kicking in. And the rule is that the components of the system and the protocols run under the assumption that the membership is fixed. And so you design a protocol to be correct using unchanging membership, but they also have to maintain a safety property that essentially allows us to terminate those protocols if the view changes. And so if a crash occurs, someone wants to join, you notify the group membership service, GMS up here, all CNI, and what it will do is freeze the current epoch, work with the protocols to clean up and terminate whatever was still pending, state transfer if needed, and then restart. And that can usually be done in a couple of milliseconds. Think of it as a 30 millisecond hiccup, which, is no big deal. Although with a 100 millisecond time budget, you'd think about it, whether it's a big deal or not. But that's the sort of time delay you're talking about. And then within it, the protocols are very simplified, actually, because they can assume that everyone knows the membership. You can do things like a round robin ordering rule, introducing null messages. You can have guarantees of agreement on such things. It's quite easy to program in a virtual synchrony model. And you can guarantee that partitioning failures won't occur. So here's that air traffic control system. And all we do is we introduce a health monitoring service, which also reports on membership changes. And this is widely standard as an architecture by now. Anyone who uses the Apache Big Data Framework for cloud computing, Zookeeper, which you've probably heard of, is the universal source of truth for who's in the system and all the configuration parameters associated with it. Zookeeper doesn't run very fast, but it doesn't need to because it doesn't happen very often. And there are similar services present in many kinds of systems. Some people use Raft for this purpose. Paul asked me about Raft the other day. It's a popular protocol. It's done by John Ousterhout at Stanford. It's not a fast protocol, but it was intended to be very modular, very easy to understand, although arguably it's not so easy to understand. And correct, although definitely it was not correct at first. Dalia Malki had to sort of step in and help them debug it. But many people use Raft. I think Zookeeper is probably 1,000 to 1 more popular in this role. Anyway, we put such a service into the French air traffic control system, and suddenly everything is clean. What would it do in particular? For example, we need agreement on who's the primary and who's the backup. And we could have more than one replica, of course. Well, in a normal system, if a timeout occurred on the primary, you might just roll over to the backup without, unilaterally. But that could lead us to believe that there were 2 air traffic controllers in charge of some flight. This kind of a system, who the controller is usually a derived side effect property from the membership view. Who's the primary? That's, you read it out of the membership view, and when the primary recovers, it gets added back in as a new backup who has most of the state. Send them a delta, that's the state transfer, and now the old backup has become the primary, the new primary is the new backup, and everyone knows. And so as you can imagine, it's very simple to build systems that way. So, there's some takeaways from the first part of this. I just have a couple more slides, which is that if you're purely temporal like CASTI is, it's extremely hard to be correct about these things, which are safety properties that absolutely must be maintained, because CASTI is fundamentally pretty probabilistic. And when we squeezed it that way, those probabilities of correct behavior actually became kind of small. A purely deductive logic would work, but wouldn't be able to respect things like a 100 millisecond deadline. We wouldn't have a basis for doing the analysis. By combining the two, though, and understanding the primacy in some sense of logical consistency for things like membership, you can get an architecture that works. So sort of towards wrapping up, what we've been doing lately at Cornell starting around 2015, May Milano, who's now this professor at Princeton, she's going to give a talk at one of the TAP sessions in about 2 weeks. No, I guess it's in 6 weeks. May and I started talking about whether advances in networking and advances in temporal logic, and the languages also, C++ in our case, might have set the stage for revisiting these old kinds of services, kind of thing that people, as they get close to retiring, play around with. And so we decided to do it. In a way, May led the engineering side of the project, and I designed the protocols and the proofs. The previous systems, I always built them, but I don't write that much code anymore. So May ran this whole operation, got used to playing the professor role, but in fact, still at Cornell. And we built a system called Derecho, and it's in C++. It's a software library. It's open source. Anybody can have it. And it's extremely professionally built. The term Derecho is a reference to a type of straight line wind that we get in the Midwest, and we've occasionally gotten them up here in Ithaca, where just this extremely powerful wind is blowing. You want to stay out of its way. And the connection being, modern networks have become so fast and so reliable, if you use them in the correct way, that you should just stay out of their way. You send data asynchronously, you don't wait for round trips. And instead of a pattern like you see in Paxos of two-phase commit kinds of behavior, what we do instead is we start to think in terms of streaming control data, streaming data on the data plane, and just sort of asynchronously reaching deductions about the advancing knowledge state of our protocols. And that's exactly how May and I designed the core of Derecho. I built my protocols that way. She designed the kind of high-level knowledge language, if you want to think of it that way. Sagar Yah, the first person on that list, built the core of the architecture, and the combination really worked. And Derecho is crazy fast. It's hard to even get your arms around how fast this system turns out to be. We run it at 75 million broadcasts a second, or 8.5 gigabytes per second. This on a network that can only run at 12.5 gigabytes per second. You've heard about 100 gigabit RDMA. That's what we're using here. Now they have 200 and 400. I should rerun these experiments. It would be even faster. The protocols can keep up with that kind of speed of the network. The 75 million events per second, think of your random Paxos protocol, Raft. Raft can probably run at, 7,500 Raft multicasts per second, and it would for sure be topping out around then. So these speeds are ridiculous, and it's hard to believe that this is really doing the same thing, but it in fact is. These are provably equivalent protocols. In fact, it's an even stronger form of bisimulation than what Leslie Lamport considers to be the gold standard for claiming that something is a version of Paxos. To the point that Leslie considers these protocols to be virtually synchronous Paxos protocols. He said I could call them that if I wanted to. And I pointed out that actually I invented virtual synchrony before he ever did Paxos. And he said, no, there's a relativistic frame of reference in which. I asked how he was sure of that. He said, well, he never read anyone else's papers, so there was no causal connections. So anyway, so this is based on RDMA, of course, but however, in fact, Derecho is fast even on TCP. It's even fast enough that it would be publishable just in that way. It gives you some sense, you're sitting in front of a computer that probably has 8 or 16 cores. These protocols can make 16 replicas on machines in a server rack faster than your computer can make 1 replica on your own machine just in DRAM. And that would be true even if you were on the fastest desktop you can get. Protocols are provably correct. We formalized them several different ways, using distalg that I mentioned, Annie Liu's system, using something called Ivy out of Tel Aviv University. We haven't used a Coq prover yet, but I have a project with Princeton and Stevens Institute of Technology to use Coq to build them constructively because we think we can do even more interesting things with proof at that point. As a practical matter, you can see the benefits. So here I've got Kafka, which is a very popular pub sub tool. That's the gray bars. It's on 1 or 3 replicas because it's a server configuration. And here we built the identical kind of system with Derecho. The little circles, those represent median delivery times. And you can see there's not much of a distribution faster than the medians. You can also see that the Kafka is getting slow with 3 replicas for 1 kilobyte messages. And then we work our way out 16,256. This actually is a logarithmic scale, so that's almost a 10-fold slower. You know, it's a significant thing. But look at the tail latencies; they're ridiculous. So in one case, it's a factor of 1,000. So with Kafka, you send a 16 kilobyte message. It might get through almost as fast as Derecho, but it might take 1,000 times longer. And a lot of the mass and subsets of the distribution is up there. And here's the equivalent 3-member Derecho. Look how tight the distributions are. And, you know, people have trouble getting their arms around this. I mean, look at this and say, you must be doing something that isn't equivalent to Paxos, because how can you be thousands of times faster than Paxos? We've worked on it for 30 years. And the only answer I've been able to give people who raise this, we've had actually papers rejected by people who say, I don't know what's wrong with this, but it can't be right, from major conferences, because they say it's just too fast. They must not be doing the equivalent thing. If they asked Leslie Lamport or Dalia Balki, they say, no, it really is that fast. Edith Kedar, famous theoretician on this stuff over in Israel, she would have said that the theory predicted this starting around 2006. We're just the first who built it. In fact, we can even prove that the Derecho protocols are optimal using a knowledge path length argument that Edith Kedar and Alex Schreier formalized. But the simple intuition is basically that, you know, in a world where you walk on gravel, there's a limited speed that you can achieve. And in fact, the constants back in the 1980s and 90s were such that round trip latencies were pretty good compared to throughput, as it turned out. Packets were small, and then they were using delay for flow control. If you redesign your protocols, but you understand that they're going to run at very, very high data rates, you design a different protocol, and it solves the same problem. It's just implemented differently. Now, more recently, we've been turning this into an infrastructure for AI. I mentioned that when I introduced myself. I'm dragging this out too long now, so I'll just be super fast about it. Cascade is the name of the system. The idea here is to run AIs and machine learning tools, but especially inference and large language model interactions, things that could run on the edge, and they might not be doing much iterative learning. You want them to be ultra fast, right? If you have an image, and you want to, I don't know, tell the driver of a car, this is the path ahead in the fog, you better paint that on their windshield right away. So you want very, very fast machine learning for those kinds of ideas. Okay, well, cows are probably not as fast as driving a car on a foggy road, but it turns out dairies need speed too, because dairies often have 2,500 cows, and they're walking past to go get milked. You would like to do a body condition score on your cows and identify the cows in a fraction of a second. We actually can do that. When we run the identical AIs on a standard cloud, this one is on Azure using standard tools. Particular tool is Apache Flink. Lots of people use those tools for lots of purposes, but they definitely aren't getting very good real-time out of them. Or I shouldn't say real-time, very timely behavior out of them. We also support things that are more plausibly real-time. Here's an interesting one, given your interest in causality. This is animating. So let me start by saying I did a project with the ISO New England, which is really a regional bulk power transfer for about 22% of the US. the northern, the quantity. There's a bit of an argument between ISO New England and New York ISO. They don't even agree on whether ISO belongs at the front or the back of the name. This particular project tried to talk to both of them, which apparently is unheard of, and also to NIPA, which brings power down from Niagara Falls. We helped them build a backup state estimator for the whole region, but then they wouldn't let me show an animation of the real system in use. We compromised and came up with the fakest looking bulk power grid conceivable. A normal bulk power grid circuit diagram looks like a simple circuit diagram. This looks like a regular, mesh. It's the real system though in use. And in this mesh, we have 20 by 20 synchrophasers, power grid sensors, sending 20 measurements per second over, that would be 400 TCP connections, but we have to use double for fault tolerance. So it's running over 800, or you can even triple if you wanted, TCP connections into a cloud where we realign the data, and then we can generate this kind of a GIF by taking, in this case, it's taking 4 of those frames per second, every 5th frame, and graphing them. And this is on the Apache HDFS Hadoop file system, which is the standard for most AI. And what you're noticing here is that if you do that with a tight time constant, and remember, think about CASD, trying to squeeze CASD and how it fell apart. And the same thing happens here with HDFS. If it knows that it has snapshots for every 5th frame, but if you ask for the data very quickly after the data arrives, but after making the snapshot, HDFS doesn't correctly synchronize internally, and you see dropouts, and the way it compensates is by giving you old data, and that's why it's so noisy. And some people think, oh, machine learning does best with noise, but that's nonsense. Machine learning can't run on that kind of garbage. Here in the middle, here on the right, I really should say, is truth. This is the GPS simulated data we encoded into our synchrophaser measurements. If it looks like a wave in water, it's because the power equations and the water wave equations are the same, Kirchhoff's law. And here in the middle, we're pretending that we don't have accurate GPS time on the synchrophasers, and we're using the time when data arrives on our cluster. But the cluster, there's a TCP connection involved, and so that's the slight scintillating effect you see. And here's my last example. Traffic intersection in a place like New York, you get cameras. You run a complicated AI. First, it figures out what's in the image. Taxis, cars, people, some sort of weird construction activity. So that's the green guy. Once you know you're looking at a taxi, you can predict its likely trajectory by having a model of how taxis behave. It helps to know if the taxi's occupied or not occupied, it turns out, in New York. The unoccupied ones tend to dart across the street occasionally. You can tell from a light on the roof. And an AI could do that, all right? So this is the trajectory projector for one of the taxis. And for each thing you identified in this picture, each agent, we're calling them, you'll have one of these pipelines. And then as the trajectory projector emits future points, and it's kind of a cloud, you can run in parallel with it, you can run a collision detector. And the idea is to sort of light up the poles red or something if a detection is imminent. And what you can see here is that when we mocked up this AI and ran it on Azure, PyTorch components and stuff, it took about 8 seconds, which is crazy. You're never going to be useful. You can't detect that an accident is imminent 8 seconds after it happened. However, we're getting down into the right range with our system. So with Cascade, here's the green. This is the execution time of the green AI, the red and the blue. The AIs are pretty fast. The little time gap there, that's Cascade running, takes a couple of milliseconds. And with slightly faster hardware, we really can do safety for urban intersections. And we did something for conversational chatbots. These are 4 different ones. They tend to also be networks of AIs that talk to each other. This one summarizes something and then translates to different languages. This one over here captions an image for children. So you have to check that you produced output that's age appropriate. Then you can output it. A QA, but again, with a check for toxicity in case someone's trying to fool the chatbot into saying something nasty. And then a driver's assistance tool that uses a vision step. And we ran it on Cascade, and this time exercising a scheduler. And what we found was that we get less slowdown and more fairness for mixes of these jobs, and with half the hardware than with classic ways of scheduling. Slowdown factors are shown here. So this would be this guy here, the green bar, is a 63-fold slowdown compared to running on idle hardware when a mix of those chat tasks are occurring under heavy load. Bottom graph, here's light load. And our version slowed it down by a factor of 1.8. You see, even as low as no slowdown at all, but under light load. So that was the talk. And I gave it the other day, and I just left with an open question. Applications need real-time. Where do you want to be on the spectrum? You want hard real-time only? You get CASD. Logical consistency, how do you know you achieved your goal? You want mixes of both. Google did that with Spanner, but it lost its speed. But we didn't really get a chance to talk about those questions. And in fact, that was what Paul said, let's pick them up here. So thank you. Now you've seen the talk, and I'll be happy to hear your thoughts.
So Edward, you had your hand raised first. Why don't you be the one that asked your first question?
But actually, I have a very, very kind of fundamental question, which has to do with, this goal of getting state machine replication, and particularly in the context of the air traffic control problem. I mean, one of the things that we have realized is that that it's possible to relax consistency in a measured way, in a way that consistency is only temporarily sacrificed. And you can bound the period of temporariness with which you sacrifice consistency. And the benefit you get from that is improved availability. So, but in the air traffic control scenario, the question arises, well, under what circumstances could you relax consistency? So there's this premise that every viewer of the database has to be able to see the same state of the system. But that's not actually true. And the reason it's not true is that if you have two physically separated processes, like two airplanes that are 20 miles apart, there are certain predictions you can make with 100% reliability, right? You know that these two airplanes are not going to collide within a certain amount of time in the future. So this ability to predict in the future actually gives you an ability to relax your consistency requirement, so that, if you send out a time-stamped event that says this airplane is going to, change altitude by 1,000 feet, that's a time-stamped event. There's observers around the system that don't need to see that until a much later timestamp, because it's not actually relevant to their actions until a much later timestamp, because they're able to do prediction. So why couldn't you design a system around that principle and just do away with this state machine replication nonsense?
Yeah,
I mean,
Paul asked a question a bit
system
like
that's physically spread out doesn't have state.
So
We know that
saying,
from quantum mechanics.
what you're saying, Edward, is one manifestation that the database imposes intrinsic intimacy that is not required in these systems.
Exactly. This is a database view of the world,
which is
and the
broken.
world
I'm a
isn't a
database guy,
database.
and I'm apologizing. What the hell was wrong with us when we thought about distributed databases?
Well, I mean, I totally agree with that. I think, and Paul you asked the same question, as it turns out, the other day. He didn't ask you quite the same way, but he asked basically the same question. In fact, there are distributions of behaviors. As you're saying, they're really distributions on the reliability requirements, and where you can say the consistency bound for events, that are close to each other in some sense, close to conflict, has to be tight. If they're far from conflict, it may be adequate that that you have a very relaxed view and you have plenty of time to fix things. Totally agree. I think the trouble is it's very hard to verify a property like that. It could be, if it could be done, though, I think it would lead to much better systems.
But there's a whole
I think
notion
you're
of a
right, but I
database.
think that's because we don't have the right software frameworks for talking about this, for actually giving you a mechanism for explicitly relaxing consistency in a measured way.
I also think, to your point, Edward, one of the specific ways this, like why this manifests in the database community so much, has to do more to do with a replication that in some ways, if you think of some of these properties as being owned by a reference frame, there's some sort of origin reference frame, like from a sensor or this kind of thing that it's truly originating from. When you start talking about non-collocated data, like you've essentially virtually said that this thing, the information that it possesses, the ownership of some physical object, actually exists in multiple locations. Because of that, it makes it harder to reason about the origin reference frame of it. It no longer inhabits a single reference frame, and that's why you can get these types of corruptions and that kind of stuff. But when you speak to this, that there are many cases where there's some piece of data where even when replicated, those are non-intersecting groups of reference frames that between each other, they don't care, and they don't run into that problem. And that a lot of the database problems specifically are when the size of epsilon is greater than the distance between the two things that are communicating.
So another
I'm wondering
manifestation.
if you could have like a multi-resolution perspective on a system where you still would have hard constraints, but the scale of the constraints could be very high resolution.
But it's the act of trying to view it as a unified database that you're doing reads and writes to, right? Write is wrong, read is worse. And so the paper that you cited, the dangers of replication in a solution, well, it got cited a ton. It implies that the database stretches. It implies that that's useful, and it's only useful if you use it in a stylized fashion, which actually gives ownership of a subset of the data to somebody who's kind of the master, or you could superimpose solutions on it. But when people in general assume I can change I can read any record and write any record, that doesn't stretch. And so, one of the problems is that von Neumann and Newton have a perspective of locality and immediacy, which works in the small at a location. But when you stretch distributed systems, it becomes like
No, but I'm suggesting one way to do what Ed had in mind is to give back a read and say, I have high confidence that the value is between A and B, but not give you a firm value. And then later, when you're under greater imminence, of a conflict, you could do a second read and say, I need an accurate answer.
But I get it, but now you're making it that much harder for the programmer to reason about when the data is solid and when the data is gushy and when does it get bound.
Well, I think that's why we don't
formalizing encapsulation.
There's a much simpler way to do it. Okay, the much simpler way to do it is that if you have, so you have this source of information, time-stamped information. The airplane is going to change altitude by 1,000 feet. Okay, and you send it to a whole bunch of recipients, and some of those recipients are responsible for a region of space that is 20 miles away. Then you simply increment the timestamp on it, and for that destination, it will process things in timestamp order, okay? But it will simply process it later, and it's okay to process it later. It has to know that the timestamp was incremented, so you have to carry as a payload the original timestamp, but the timestamp order processing will be based on the incremented timestamp that is dependent on the ability of the recipient to do prediction.
I don't know if that would be easier, but I can see why it might work. So I think that it would be a very interesting sort of programming languages, distributed systems exercise to ask what you could build against these other kinds of models. And I think it would be very worthwhile if people are going to do increasingly robotic systems that maybe have to cooperate or interact at various. It's a good direction to pursue, because a sort of one size fits all solution. Well, a good example is Google Spanner integrates notions of time and notions of logical consistency, but it's terribly slow.
Because
It's
it attempts
widely
to
used,
emulate a
very slow.
centralized database in a way that's kind
Right.
of goofy. Have you,
It's
how familiar are you with?
strong consistency globally, and so control systems people do this as actually a matter of routine, right? There's model predictive control where the controller uses prediction in order to get very, very quick turnaround on the control. And to the extent that the prediction is reliable, it's able to do that. And you can see this as a way of sort of relaxing consistency. When you're taking action based on prediction, okay, you're using potentially inconsistent data. But to the extent that that prediction is reliable, that works just fine.
Calton Poo took this idea, this was many years ago, but Calton Poo, and I think actually also Hector Garcia Molina, did work on a variant of this, where what they said, the example that they were using was old days. They said, suppose that I almost always get my money from my bank account at one particular ATM. Well, they're worried about disconnections because with modems, we used to have trouble with the dial-ups and stuff.
No
So they
shit,
said,
you had a modem.
couldn't I put $1,000 of my money sort of held by that ATM? Now I'm allowed to take out up to 1,000, and everybody else knows that the balance is somewhere from X to X plus 1,000, but that last part is locked down and I can't touch it.
The variant
So-
of escrow locking. Yes.
Yeah,
Right.
so there's a wonderful paper I'll need to dig up on this subject that was trying to describe all of these problems in terms of a distributed semaphore, because it's a really good toy problem that can represent exactly that, where it's kind of absurd that you would need to totally order every operation on a semaphore with a very large value, but how do you geo-distribute the existence of every single ticket in the semaphore? And distributing them as tickets gives them this idea of non-fungibility that doesn't actually exist. All of them are actually interchangeable. And I really appreciated the framing of it, because I think it's a really clean way of viewing exactly what we're talking about, where it's easy to
you would
confuse.
there's a paper out of MIT that was published at SOSP. It was on sloppy counters for distributed kernels. And the idea was semaphores, it was counting semaphores. They made the point that if you were doing, it was for distributed cache coherence, that the cost they were worried about was that you had a lock, and but it was a multi-core system, and you had multi-core consistency slowdown effects from the hardware. And they said, well, if some core, which might have multiple CPUs on it, has at least one instance of the lock, we don't have to keep track of whether
This is a variant of, they're putting commutativity in there within bounds, right?
right. And then
If you-
when it would drop down to 0, then we would tell everyone else and incur the distributed. But it was good enough that everyone knew that, well, there's a count that's non-zero.
Right. So I wish people would read the linearizability paper, because it says if you have an abstract data type that supports high concurrency, you can actually stretch the visibility of the clients and the behavior of what you know and when you know. But it starts predicated on a highly concurrent abstract data type, which is not
actually,
read and write. It is not read and write. And so
Mark Shapiro's conflict resistant
is a variant of that, no doubt about it. I disagree.
Too, right.
But the thing about CRDTs that I'm not a super fan of is they assume an infinite replica of these things are viable. And so that means that you get into the calm conjecture kinds of notions of confluence that can't speak to does not exist because of the unbounded. I can find a replica behind a rock and I don't know what it's got in it when I find it 3 years later. But if you superimpose that with quorums, then you can make statements about what conquered the quorum, which is partially what Leslie observed in Paxos. So we're not doing a great job in talking about the abstractions of what we're trying to do. If you want to take reads and writes, you're doomed. You're just doomed.
Well,
because
to me, the proof of that was when we tried to get the Derecho. We did get it published eventually in Talks, in a good journal. But
you start with a state machine
tried,
replication. State machine replication means I got an exact image of the gosh darn thing, and I can
well,
do
no, except
right.
that we built it completely on an asynchronous sort of temporal logic framework. And people looked at this and they said, well, I've seen these concepts in other contexts, but put together this way, this is pretty weird. And it took a long time to get that paper accepted because we were just coming at it from a different, and all we were trying to do was say, well, let the data flow, let the control data flow, and just do asynchronous inferencing off the
But what you
stream.
didn't state was the actual interface to the state machine replication. Just saying state machine replication implies, you know, basically at least a DFA, right, with a crisp deterministic behavior. Now, you could superimpose on that I've got a window of non-determinism that reconciles within bounds and defining that, which at some level is sort of the CRDT stuff. But just saying state machine replication to me means the worst pessimistic case of I have a predictable next thing, which means strong consistency of some behavior of that
You know,
state
and if you
machine.
take Ed's point to its limit, I think about this sometimes. I have never figured out how to approach it. Biological systems obviously start probabilistic, but behave deterministically at large scale. And in fact, it's true of physics too for a lot of things. You know, you get these quantum phenomena at small scale, but somehow it's totally deterministic at large scale. That we don't understand that transition in a mathematical sense very well at all.
Of course we don't, because we haven't defined what it means. We haven't defined what the behavior of these things are. And starting with read-write state machine replication kind of puts you in a corner where you're limited.
I wonder if we even have the right math framework to pose these questions in a way where it feels like the answer ought to fall out, right? I mean, unless you got arthritis or something, you can do these complicated things with your hands. And it was extremely hard to understand how that could be and why it's so fault tolerant, you know?
So
And yet
I got really excited by a recent set of papers that I think, you know, Paul, you know exactly what I'm talking about for sending you the common knowledge regained and some of those perspectives. That I believe that some of these early logic puzzles you're talking about, basically like the whether it be Byzantine general problem or two generals problem, this kind of stuff, actually trying to come up with engineering solutions to these or reasonable answers to those problems give a good indication of what useful mathematical frameworks exist. So the common knowledge regained paper basically spoke to how common knowledge its usage of sort of this mix of epistemic and temporal logic doesn't make a lot of sense in the physical world because it assumes some sort of global time. That it is the basis assumption was that you can't come to common knowledge without pre-existing common knowledge because common knowledge requires exact simultaneity. And if it exists in an asynchronous system, any amount of timing frictions prevent simultaneity. If you have any amount of variance, that you can't even come to common knowledge over the receipt of a message, even if it's guaranteed to be delivered. You never reach common knowledge because if there's a timing invariant, you know, that you don't come to the knowledge at the same time. But most of all of these fun logic puzzles came out of the fact that you were assuming that there was some global time in the first place. You can't have common knowledge if you can't have simultaneity.
Well, here's a twist on that. I didn't really get into it because I realized I was running much longer than I wanted to. But with virtual synchrony, you act like the membership view and all sorts of other stuff actually is common knowledge. So when you introduce the beginning of a new epoch, you have this relativized form of common knowledge that you just start to act like everybody knows what the view is and everybody knows that everyone knows. And you literally write code that's correct under a common knowledge formulation, even though you know that they cannot possibly be correct because they can't achieve common knowledge.
What you're referring to precisely is the common knowledge solution co-occurrent knowledge. Because it's not that, oh, this actually is guaranteed to achieve common knowledge. It's that basically no actions would have actually been taken if this knowledge doesn't exist.
That's right. That's right.
If you're not a member, it wouldn't have happened in the first
common
place.
knowledge with a separate mechanism that's going to basically murder anything so you if the system makes progress, it makes it under a common knowledge, indistinguishable from common knowledge behavior. And otherwise it doesn't make progress, and so you're safe either way. And it's strongly safe. It really works. I wrote a whole paper about this. It's a weird paper in a weird place, but I wrote a whole paper about it.
I think one of the reasons that this is so difficult to reason about is that as soon as you give up this notion of simultaneity, you also have to give up the notion of system state.
Mhm.
And so when you talk about, yeah, I mean, the way you just phrased this, Ken, was talking about knowledge about the system state.
There is no system state. There's
We
subjective
actually, I
state.
think, to really get our handle on distributed systems, we have to give up on the notion of system state.
Yay,
It
verily.
doesn't exist. Okay. And I think that's a very difficult thing to do.
I agree. Subjectively, I'm the center of the universe.
Mhm.
I don't know about you guys. You're beyond my event horizon.
I think that's totally valid. Actually, I agree with that. Capitalism works that way too. We achieve some sort of a goal. Hopefully it's a reasonable goal by acting in a self-centered way.
And that was a wonderful conversation. Really appreciate everyone's intense interest and participation. Thank you.